So I'm really happy here to introduce Professor Henry Segerman from Oklahoma State University, low-dimensional topologist, specializes in three manifolds, geometric group theory, and also visualizing mathematics. I think many of my own ceramic works are also like really inspired by his work. A bit unfortunate we cannot have him to come over today, but we have some of his work, like the 3D printed ones, like the knots here. Like I think these are distributed. You can have a look, and then maybe Henry will tell us more about this in a minute. Yeah, just please get started.
Okay, thank you. So yeah, this is a talk that I give to almost to any audience. I mean, it works at the very high level with mathematicians and topologists and students, and all the way down to high school students. I've given it to high school students as well. And this is really going to be looking at lots of the sort of work I've done in mathematical visualization. But I sort of start off with this I often start off with this question of, isn't it a strange combination of things to be doing mathematics and art, and sort of try and maybe give people an appreciation of how they're maybe closer than you might think. So I'm just going to start off with a slide of, what does my sketchbook look like? And this is probably familiar to topologists and other mathematicians, that what research looks like has a lot of pictures in it. And maybe that's the first thing that people might think of as a relationship between mathematics and at least the visual arts is, okay, it's not just numbers and equations, there are also pictures, and pictures are visual. And so maybe that's the relationship between mathematics and art. But I think there's a closer, a stronger relationship, which is that both mathematicians and artists are allowed to ask what-if questions. So if you're a scientist, if you're an engineer, at some point what you're doing has to relate to the real world in a real way, right? If you're a scientist, eventually the experiment has to confirm your hypothesis. If you're an engineer, the bridge has to not fall down. But if you're a mathematician, you can just dream up some other way that the world could work, or the way that the objects that you're interested in might work. You could change your axioms and see what the consequences are and see what happens. And that's also true for artists. It's okay to just make things up, go out into the wilderness of what might be true. But it doesn't have to be real for it to be valuable work. And so as I say, I think there's a closer connection between mathematics and the arts than you maybe might at first imagine. So most of what I'm going to do today is just show you a whole bunch of pretty pictures and tell some stories about how these different bits of visualization or art, depending on how you want to think about it, so where did they come from and what's the story and so on. So I'm going to start with this slide here, which is a 3D print illustrating one of the key examples from three-dimensional hyperbolic geometry. This is the complement of the figure-8 knot. So what you're supposed to think of here is I have a ball of dough, and I have a very well-trained worm, and I've trained this worm to eat out a knotted path through the ball and out the other side. And what remains is this three-dimensional manifold, the complement of the figure-8 knot. And this is, as I say, it's the first example you test anything on if you're doing hyperbolic, three-dimensional hyperbolic geometry. And I should mention, of course, so I won't always mention the people's names of people that I've worked with, but as with pretty much everything else that people do, it's more fun with other people. And so I always have the credits for people that I worked with on whatever it might be, somewhere on the slide. So here's another classic topological idea, or I guess the joke about topologists is that topologists cannot tell the difference between a donut and a coffee mug, and of course here's this sort of deformation showing that these 7 objects are all really the same. I am a topologist, so I can't tell which is the donut and which is the coffee mug, but people who are not topologists tell me that there's No. Anyway, so these are all printed in ceramic material. And so this one was joint work with Keenan Crane, who's a computer scientist at Carnegie Mellon. And the sort of mathematically difficult, or the mathematically interesting question in coming up with this design is, where do the shapes come from? And it's all very well for, as a topologist, to say, oh, everything's very floppy, and you can deform things as much as you want. But the printer and the computer that runs the printer needs to know exactly precisely where the shape is. And so how do you, as a matter of fact, come up with these shapes? And so Keenan Crane is in discrete differential geometry, and he's using something called conformal Willmore flow I think he started with this design here, and then ran the flow on a mesh of triangles to get it to deform back to this thing here. And maybe you'll notice, you can see a little bit of the process here. This handle on the coffee mug is very thick. It's much thicker than you would really want on a usable coffee mug. And the reason that it's so thick is that he had to do this in order that at the end he gets the round symmetrical torus. If it was a thinner handle here, then I think this would you'd have a thinner patch on the torus here. So we had to do it this way. Here's another classic object from topology, the knots. Of course, you tie the knot and you have to close up the ends of the knot to make a closed loop to sort of trap the knot. This is a very special shape. It has an extra property which is not at all obvious from when you just look at a still picture of it. So here's a video showing that this knot rolls along the table. So this is an example of a knot configuration. In fact, as far as I'm aware, the only example of a knot configuration that has no tritangent planes. There are no planes that you can hold up to the knot that are tangent in 3 or more places. So this is only tangent in at most 2, and that means that there's never a stable point. If there are 3 points of contact, then that would give you a triangle that presumably it would be stable on. But since there are only ever 2 at most, then it just rolls around. As far as I'm aware, this is, as I say, the only known example of this, and it was discovered in the 90s, I think. But if anybody happens to know of any other shapes of knots that have this property, obviously I would like to know so that I can make sort of rolling versions of them. Here's a much larger rolling object. This is me inside of a big metal structure. So this is, I guess, an exploring and expanding class of circus performance art. So Lee Brazzawell is in the Department of Theater here at Oklahoma State. So I met him at one of those faculty meet and greet things where they tell you boring things for an hour, but it was worthwhile going to this thing because I met Lee and found out that he has an interest in circus arts as well, and so we got working on this project, and he does rigging and constructing props and so on, and so we ended up making this thing here. So I'm not an acrobat, so I'm not going to show you a video of me trying to use this thing, but this guy, this is Chris Delgado, he does know what he's doing inside of this, and so in this video he's sort of showing you what this design does. So this class of circus performance art, so you get inside of a big metal frame and you roll around on the stage, and you're rolling upside down and so on and so forth. So the most common of these is maybe it's just a wheel. It's just a big metal wheel. It's called the German wheel. And there were some other variations as well. And so the sort of question was, what else can you do with this art form? So in this one, you can see Chris is showing off sort of how this works. So it will roll in a straight line, but there are certain points in the motion where if he shifts his weight in a particular way, then he sort of shifts lane, and so you're rolling along, and then you could shift lane to be rolling along another parallel path next to it. And so the mathematical question is, how do you design the rails to make that possible? Ideally, with as smooth as possible a ride, that you can make. There's also not immediately obvious, but one of the constraints that you want to stick to is you don't want the center of gravity of the shape to change, right? You want the center of gravity to be at constant height as this thing is rolling around, because if it dips down, then it's very difficult for the performer to get out of a valley and back up a hill. So there's actually wrote a paper in the Notices of the AMS, which explains sort of how this works and some of the mathematics behind this. So let's transition to other things that roll. I've thought a lot about these transitions to try and connect these things together. So dice are a very famous rolling kind of object that people are familiar with. Well, maybe not familiar with these kinds of dice. These are extremely large. Well, I guess they're not extremely large. They're about this big. So, you know, a lot bigger than an ordinary die. These are the first commercially available mass-produced 120-sided dice. So you can see the 120th face facing us here. So the shape here is maybe you can see it's sort of a cross between an icosahedron and a dodecahedron. So there's one of the 20 triangles of an icosahedron, and then I can also draw here one of the 12 faces of the dodecahedron. And so you sort of put the dual icosahedron and dodecahedron together, and then additionally add some mirror symmetry, sort of splitting it an extra time, and it turns out you get 120 faces, and the shape is the symmetry group is transitive on the faces, which is what you need in order to make the die fair. So I've been working with for many years with Robert Fathauer to design and make mathematically interesting dice. And this was actually one of the earlier ones we did, which was to make these. You know, nobody had done it before, and so we said, okay, somebody should do it. We were joined by Bob Bosch on this. He's in operations research at Oberlin College. And so the reason that we brought Bob in was to deal with the numbering, or how do you figure out where the numbers should go. So so an ordinary 6-sided die is a cube. And if you've looked at a cube, an ordinary 6-sided die, you'll probably have noticed that the 1 is opposite the 6, and the 2 is opposite the 5, and the 3 is opposite the 4. So that is opposite numbers always add up to the same value, or said another way, the average of two opposite numbers is the same as the average of the numbers over the die. And it's not entirely clear why that is the case. That you know, you won't find many dice that don't follow that rule. The historical scholarship is not there apparently in dice production. But one, I think, very good theory for why it should be that dice are sort of balanced between the opposite sides is that one way in which a die can be sort of imperceptibly unfair is if you take the cube and then you just squeeze it down a little bit to make it more like a coin. And if you do that, the two sort of larger faces are going to come up more often than the faces around the side. And as I say, I mean, it can be really difficult to tell. Like, you can't tell just holding one of them that it's been squished a little bit, but it can change the probabilities by 10% or so. And so by making by balancing the numbers over opposite sides, that's a way of sort of ensuring that even if the 1 and the 6 come up more frequently than the other ones, at least the average that you roll will not be high or low. So it's a sort of balancing rule. So, okay, so obviously we'll follow the same idea. The 1 is opposite the 120, the 2 is opposite the 119. But that still leaves a lot of possibilities. And so what we decided we would like to have is we want to sort of like more sorts of ways of evenly spreading the numbers out over the die. So for example, it would be nice so here's a vertex of degree 10. It would be nice if the average of all of these 10 numbers is the same as the average of the numbers over the die. And here's a vertex of degree 6. It would be nice if the averages of those 6 numbers, or any 6 numbers that are arranged around one of these vertices, should be the same as the average of the number of it. I guess it's 60.5 is what it should be. And you might also want the average of the 4 numbers around every vertex of degree 4 to be the same. And so we do achieve all of those averages at the same time. And this is not an easy problem to solve. Working with Bob Bosch, we recasted it as an integer linear programming problem. And after a month of Bob working away at this, he was able to find a solution to this. Since then, I think, yeah, so we've just over the past half year or so, we've been talking with a guy, Paul McGuire, who's been using genetic algorithms to try and find more solutions to the numbering problem. And the number of solutions is now in the millions, or I might be off by a few orders of magnitude. He might even be in the trillions now. But we really don't have an idea of the space of solutions to this. So there's still sort of more research to do. How many ways are there to number a 120-sided die so that with all of those balancing properties? Anyway, so here are some, I guess, simpler versions of, or simpler distorted dice or dice that we've produced. So these are, close to the ordinary 6-sided cubical dice, but they've been distorted a little bit. And well, I mean, I guess don't take these to Las Vegas. It's probably not a good idea, but you might ask, and people usually do, are these fair? And so let me convince you that they do have the symmetry that you need. So here you can see that the three faces that you see here have an axis of threefold rotational symmetry. And then if I turn it around, then you'll see that the other three faces are also exactly the same. And so yes, this is at least the idealized mathematical shape has the symmetry property that you need. Or in other words, I guess another way you could say it is that this has exactly the right amount of symmetry to give a fair die. The ordinary cube has an excessive amount of symmetry if all you need is for your 6-sided die to be fair. You can do the same thing with 12-sided dice. It's a little harder to tell, but maybe if I sort of draw this on here, you can see this is not a regular pentagon and this is not a regular dodecahedron. I think it's sort of harder to tell because people don't really know what dodecahedra look like. Like everybody knows what a cube looks like, and they know that this is not a cube, but it's sort of harder to tell what a dodecahedron looks like. They don't just have it in their mind, so it's sort of less impressive maybe. And eventually we ended up with the full set of 7 Dungeons and Dragons dice. So the standard set of 7 dice, there's a 4-sided die, 6, 8. There are usually 2 10-sided dice, so you can roll for percentages. And there's the 12-sided die and the 20-sided die. So the usual 4-sided die is a regular tetrahedron. And so there's a problem with the regular tetrahedron in that where do you write the numbers, right? There isn't a top face. Whereas with this distorted version, there's a very clear uppermost face. So again, we think this is just a straight up improvement. Maybe the other one to mention is the 20-sided die. So all of the other shapes, there is a way to distort very slightly away from the Platonic shape and have another fair die. So we get a skewed version of all of these examples. The 20-sided die, there is no way to do this. It turns out the icosahedron, there is no small distortion that maintains the transitive symmetry group being transitive on faces. And so it took us a very long time to accept that the only thing you could do this is 2 10-sided pyramids stuck back to back. And so it's well, it's a very unsatisfying 20-sided die, but we had to in order to make the set. So we ended up just going with it eventually. Talking of symmetry, here's a sculpture I made with my brother, actually. So this sculpture we call More Fun Than a Hypercube of Monkeys. So let me try and explain what's going on here. So I mentioned this was symmetric, and it really is. So here's a monkey, and on that monkey's head is standing another monkey, and standing on that monkey's head is another monkey, and so on and so forth. There's a ring of 4 monkeys around here, and there's another ring of 4 monkeys around here, and these 8 monkeys are all symmetric in 4-dimensional space. So there's 1 monkey for each cell of the hypercube, the 4-dimensional hypercube. And then the 4-dimensional hypercube has lots and lots and lots of symmetry, but we break that symmetry by putting this asymmetric monkey in each cell of the hypercube, and then that produces this sculpture which has the same symmetry as the 8-element quaternion group. And as far as I'm aware, this is the first and probably only sculpture that attempts to show this this symmetry in a sculpture. Here's a similar sort of thing based not on the geometry of the 4-dimensional hypercube, but this is on the 24 cell, and this one is based on the 120 cell. So this is more fun than 120 cell of monkeys. And there is also a virtual reality version of this. So you can go to monkeys.hypernom.com. Actually, I'm going to switch over there now. I can. Here we go. And show you this is the animation that shows when you go there, and you can see every few seconds this monkey is rotating around to become this monkey, and so on and so forth. And so this animation is showing one of those symmetries that this sculpture has. And if you press the number keys, then you can get the other sculptures to load. So this is the 24 cell. Whoops. There we go. This is the 24 cell of monkeys with rings of 6 monkeys here. The 24 cell you may be aware is self-dual, which means you can fit another 24 monkeys in the gaps left by the first set of 24 monkeys. And then this is the 120 cell version. Let me see if I can get to a good position. Yeah, so again, here's one of those rings of monkeys, and every few seconds this monkey becomes this monkey. And again, it's showing one of these, another one of these symmetries. Okay, let me go back to my slides. So, so I wanted to take a little bit of time to sort of just, I guess, philosophize a little bit about, what is it that makes a visualization good, or how should we judge a mathematical visualization? And to do that, I'm going to discuss this this example here, which is an illustration of stereographic projection using a light source and a 3D printed sphere, or this sort of grid on a 3D printed sphere. So, in case you haven't been not familiar with it, let me just quickly explain what stereographic projection is. It's a map from the sphere to the plane, and the way it works is that you just trace a line from the north pole of the sphere down inside of the sphere, and it hits the sphere somewhere. And if you continue that line on to hit the table, then it hits the table somewhere. And so the map is simply where does this line, where does this ray hit on the sphere, and then where does it hit on the plane. And I mean, you could write down, so maybe the first thing I'll say, why is it effective? I think there's a surprise there. How does this square grid come from this curved grid? And hopefully you draw the viewer in and you make them wonder what's going on, and then maybe you can teach them some mathematics. Stereographic projection was known to the ancient Greeks. It's older than other ways of mapping the sphere onto the plane, the Mercator projection. We'll actually see one or two other methods of mapping the sphere onto the plane later in the talk. So just by showing this picture of the light rays casting shadows, it allows the viewer to understand what stereographic projection is. You could write down the formula, but you don't need to understand the formula in order to understand what stereographic projection is. And so there's a surprise. It's explaining what it is without the need of other things, and you can explain what stereographic projection is to somebody who wouldn't understand a formula necessarily. I think there's also, it's a good idea to think about the medium in which you're communicating. In fact, in all of the things that, as mathematicians, we're usually writing papers and using theorems to communicate what we're doing, although actually that's not exactly true. We write papers, but a lot of the communication happens when somebody comes to our talk, and that's a different medium where different sorts of communication are happening. So in this case, this is a way to communicate stereographic projection using a piece of plastic and a flashlight. And there's something about the medium there that I think is good, in that you could have made this picture using entirely in a computer, right? It could have been a computer render. But the people have seen enough computer-generated imagery and these days, particularly with deepfakes and AI and all of this sort of stuff, I think people are sort of rightly suspicious of some computer-generated image or even pictures that they see on the internet. But here, I mean, again, if I were there in person, you could actually touch it and feel it, and it's just a piece of plastic and a flashlight, and you think you understand them, and so there really is something going on here. It's not just computer graphics. Maybe the last thing I'll say about this, the position of the light here is very important. So it really needs to be at the North Pole in order to get these nice straight lines. If the light moves around a little bit, then the lines become curvy, and it's very easy to see that something's wrong. It's very sensitive to the position. So this photograph was not very easy to take. I didn't, have to. Wasn't, as a matter of fact, trying to line up the position of the light very carefully with the North Pole of the sphere. What's actually going on is that the flashlight is taped onto a rod that's coming up vertically above the shot, and there's a crossbar across the top and a clamp stand either side. And the hand is purely decorative. It's sitting there trying to make it look like it's holding a torch, but actually it's not holding the torch at all. It's trying not to move the light. So why is the hand there at all? It's to make it look less like computer graphics. It's to if the hand isn't there, then the 3D printing has got so good, you can get things so precise that it just looks like it's computer generated. And I guess in a sense it is computer generated because I did design the thing on computer. Anyway, going forward with that idea of using shadows as a way to do different projections. So this is a single 3D print, this sort of hemisphere here, which gives you 3 different models of the hyperbolic plane. So if you put the light at the North Pole of the sphere, then the projection that you get down here is the Poincare disk model of H2. If you take the light and you move it very far up so that the light rays are coming down parallel to each other, then you get the Klein model in the shadow. And if you put the lights on the equator of the hemisphere, then you get the upper half plane model. As you get these very nice illustration of the connections between all of these different
models.
Now, back in 2017, we had a whole exhibition in Edinburgh, and this ran for I think a few weeks, maybe a month or two. So here we have, this is a 4-meter tall version of the grid, and this was a sort of interactive globe. So you could actually rotate the 3D printed sphere around and change the projections and change how the world looked. We had a whole room full of different tilings, and these were all interactive. There were things you could slide in and out and rotate and so on to see different things. And this was the sort of finale. This is a 3D printed zoetrope. So you've maybe seen these zoetropes. The zoetrope is sort of the earliest form of movies. So the earliest ones were you have like a cylinder, and there were slits cut in the cylinder, and you spin the cylinder around and you look through the slits, and you see on the inside surface of the cylinder pictures or photographs or whatever it is that you're trying to animate, and then the persistence of vision effect has it look like it's animated. And so this is a very modern version of the same idea. This is a disc. It's about 1 meter across, and there's a strobe that's going off at exactly the right time, so that each of the 30 3D printed sculptures is lit up at the right time, so that it appears in the correct position to do this animation. And the animation here is, of course, a hypercube rotating in space. So this is the same as the hypercube of monkeys. The animation that was doing is the same thing here. And I guess one of the interesting things about this, or designing this, I should mention, I mean, Peter Reed down here was really the expert in the timing and the electronics and getting the strobe to go off at the right time and all of this sort of stuff. I designed the 3D prints, and the sort of most difficult part of this was not, making this hypercube rotate. The most difficult part is getting these legs to connect on, right? So I can't have the hypercube just float there in midair. It has to be supported some way. But the way that it's supported isn't some, beautiful mathematical thing with only one solution. It required thinking about and, coming up with some way to decide what the shapes of these things should be so that they would, they would jump around as little as possible and be as unobtrusive as possible. Okay, so let me transition from, let's see. So this appears to be that the plastic is sort of deforming in this big way, but that's not of course that's not actually happening, right? It's this illusion. So this looks like it's moving, but actually isn't. This next item, it looks like it should move, but in fact it doesn't. So this is a photograph of a bus shelter in Manchester, England, which is actually where I grew up. And there's this graphic design element of 3 gears that are meshing together. And I think the idea here is that somehow there's different transportation systems that are coming together and working well with each other to make the city move. But if you think about this for a little bit, you'll realize that there's a problem. So let's suppose that this gear is rotating in the clockwise direction. Well, that means that because of the meshing of the teeth along here, that the second gear must be rotating in the counterclockwise direction. And then that means that the third gear has to rotate in both directions. And so, of course, it can't. It's frozen. And over here, the teachers, the students, and the parents come together, and no progress is possible. Everything is just deadlock. You can't do anything. I think this was from a middle school. I think at the university setting, we replace the parents with the administration, and then it's entirely accurate. So there's a challenge here. How is it possible to come up with a design where you have 3 different gears which pairwise mesh into each other, and yet the whole thing can move? And so, so this was our first solution to this problem. This is a little hard to see what's going on in this still picture. I'll show you a video in a second, but I guess let me just sort of describe it. So there are 3 rings that pass through each other. Here we go. Here's a video that's showing what's going on. So there's a circular ring here, and then another one that goes around here, and a third one that goes around here. There's actually a 4th part here. This is just a sort of helix. It's powered by a motor in the base of the sculpture. And as you can see, these 3 rings are sort of rotating through each other. As is often the case, the first sort of solution to this problem is not the easiest to understand. So we later produced this much easier to understand version. I guess the gears are not rotating anymore. These are translating. And I guess we've changed the topology. This is now the Borromean rings. The previous one was the 3-3 torus link. But yeah, this is the translation version of gears, so using racks instead. Here's a version with 4 different racks which are able to slide through each other, and all 4 of them are meshed with each other. And here's the current record, which is 5 gears or racks. So 5 parts which are all in contact with each other in a symmetrical way, and they all mesh into each other. So yeah, I guess talking about the medium again, 3D printing is very good for things that move. I mean, it's harder to design things that move than static sculptures, but if you're able to play with them and manipulate them, then you're getting more across than you are from just a static picture. So what is this illustrating? So this is a polygonal torus, and any geometer will tell you that the best geometry that you can put on a torus is flat Euclidean geometry. And this one really does have flat Euclidean geometry. You can see that it's flat by opening it out onto the table. In contrast, here's a negatively curved surface. So I guess this is another kind of model of the hyperbolic plane. This is well, so maybe if you look closely, some of the holes here have 7 triangles around them. Some of them have 6. So this is sort of like if you just did 7 equilateral triangles around each vertex, it turns out, excuse me, gosh, had to sneeze. So if you did 7 equilateral triangles around each vertex, then you get something that's very spiky. It doesn't feel like a smooth object. And here this is smoothed out by, it's sort of like sort of how you turn an icosahedron into a geodesic dome. Anyway, so maybe I'll just say that the difficult mathematical question here is, how did we print this? So this was printed as a single object. So I did not print out 300 tiny triangles and then somehow hinge them together. It came out of the printer like this. And so it had to go into the printer, or the design had to be arranged in such a way that that it was already in one of the shapes that this object can take. But there's no canonical nice shape for this, so how did we find that shape? So we used a sort of iterative process to do that. I got into expanding structures, so maybe people are familiar with the Hoberman sphere, this plastic linkage that opens up to a much bigger shape here. So this is sort of my take on this in the form of a dodecahedron. Using the same sort of, the same parts, in fact, this is a kind of expanding structure which is triply periodic. So the Hoberman sphere, it expands, but it's really, the mechanism is really confined to the surface of a sphere. And the sphere expands, but it's still really a two-dimensional structure. This is a really three-dimensional structure. It's the lattice here is the diamond structure of, it's the crystal structure of diamond. So the way that carbon atoms are arranged in diamonds, that's the underlying shape here. And the same mechanism again. Here's a sort of grabber object which is dexterous enough to be able to catch a tennis ball in midair. Maybe you've seen these sorts of assistive technology kind of things. If you want to pick something off of the floor without needing to bend down, then you can. Let me just play this again. Then you can get these sort of grabbers. They generally have 2 claws, whereas this has 4 that come in from all directions, which makes it much easier to, for example, catch the tennis ball. More projects involving linkages. This was a project with Kyle van der Venter, was a undergraduate at Oklahoma State in both mathematics and aerospace engineering. So he was interested in doing a project that both had mathematical interest and also something to do with mechanisms and mechanical engineering. So this is a grid of scissor linkages. It's actually inspired by the Thurston's pictures of the boundary torus of an incomplete hyperbolic manifold. This is sort of self-similar tiling. And here's a different structure with just slightly different parameters for the shapes of the quadrilaterals that become scissors here. This is another expanding structure. So this is this mechanism actually relatively well known. This is Buckminster-Fuller's jitterbug mechanism. So Buckminster-Fuller is maybe best known for popularizing geodesic domes, but he was interested in all kinds of geometry and physical, things that moved and so on. So he came up with this mechanism. Our contribution here is the gearing here on the sort of hinges. So it turns out mathematically that gearing is unnecessary. So if your joints are perfect, mathematically perfect hinges, then this object still has a single degree of freedom. However, it tends to jam in real life, like things get out of alignment and then it stops working. And the gears here really sort of help align it gives a secondary constraint beyond the constraint coming purely from the hinges, which makes it run much smoother. So there's really some sort of like, this is really starting to get into the engineering questions. What am I as a pure mathematician doing in engineering? Well, this is what happens when you try to make things in the real world. Unfortunately, this is where you end up. Here's another geared object. So these 2 gears are meshing into each other, but maybe you'll notice there are no axles and there's no frame which is holding them together. So how come they stay together? Why don't they fall apart? And here's a variant of that same design with some extra holes cut out, so you can show by passing a screwdriver between them that there's really nothing holding these gears together. And here's the follow-up version, I call this braiding gears, because the paths that the three gears take through space is a braid. You can get any three-strand braid out of these. So again, they're always connected together, and yet which one is in the middle can switch around. Here is a 1 degree of freedom mechanism. It's illustrating how you can fold a cube up from one of its nets, and some other expanding mechanisms. So this is based on the rack and pinion, or again, the racks are the sort of translational motion gears, and then there are the pinion, it's the little circular gears. Here's the exact same pieces, but rearranged in a different way, which produces this very different sort of motion. And here's a sort of the same sort of idea with racks and spur gears, these rotational gears, but then thinking about how you would transfer the sort of power and transfer motion in three orthogonal axes in three-dimensional space. And talking about gears, this is exploring a different kind of way to do gearing, which is neither rotation or translation. So we've seen rotational gears and sort of translational gears or racks. And this, as far as I'm aware, is the first example of a gearing between two objects that are both doing screw motion, which is, I guess, is the third type of Euclidean isometry. Here's some puzzles which are based on the idea of holonomy. So holonomy is the effects by which, when you go around a closed curve in a surface with curvature, you get rotated. So this little green piece starts off with its arm inside of this holder, but when you get back to the start after going around one of these 90-90-90 triangles, you end up rotated and you don't fit in anymore. Here's the follow-up version to that. This is a holonomy maze on a dodecahedron, and you think a little bit about why it is that going around a five-sided pentagon rotates the piece by 60 degrees. So again, why should it be that going around a five-sided object should rotate you by a sixth of a turn? And of course, the answer is Gauss-Bonnet. Here's the same sort of idea, but on a surface with negative curvature. And so this time we're going around a pentagon with 5 right angles. And this time when you go around the pentagon, you get rotated the opposite way by holonomy than you do when you go around an equivalent right angle triangle with positive curvature. And here's a very evil sliding block puzzle. So this is sort of, I guess this is related to the 15 puzzle, where you have your 15 tiles and you slide them around and you mix them up and you have to get them right back into the original positions again. I call this the continental drift puzzle. You start with the continents of the world and you mix them up, and then you have to try to get them back into the right position again. But now you not only need to get them to the correct position, you also need them to have the correct rotation when you get back. And let's see. So here's an optical illusion. I got interested in 3D printing in real life optical illusions. Of course, there must be a cheat somewhere. And here's the cheat. If you line the camera up in exactly the right place, then you can make it very difficult, if you get the lighting right as well, to see where the error is. This is a sort of topologist's optical illusion. So this looks like a trefoil knot, but it is not, in fact, a trefoil knot. This is the unknot. You can just unravel that, but that, again, it looks like a trefoil. And here's a similar sort of idea. You can see over here, this looks like an unknot, but in the mirror, you can see that it's actually a trefoil. And here I'll rotate this so that the mirror version looks like an unknot, and the version you see directly looks like a trefoil. Also, other ideas playing with camera and carefully arranging where the camera is. So this is a fractal zoom. So like the zooms into the Mandelbrot set, except this one is in real life. And you can also do this with a little bit more. You have to be a little bit more careful about everything to get it to work when it rotates as well. And here's a version where there's a laser on it because I could and it would look good. Okay, So, so I've shown you a whole bunch of things, but any educator will tell you that it's much less effective to just see somebody do it. It's much better to do it yourself. So, so I have a 3D printing lab in the mathematics department here at Oklahoma State, and I run a course every year, which is a sort of 3D printing for math majors course. So this is, I think, the homework from week 3. So they've learned how to use the software, they've learned how to use the 3D printers, and now the assignment is just find some interesting parametric curve and make a model of it. And it's a project-based course, so there aren't any exams at the end of it. The students are supposed to find some interesting mathematical shapes and then make them. So fractals and things to do with polyhedra. This is to do with phyllotaxis, the shapes that plants form. And so yeah, lots of other interesting ideas. These ones are based on Fourier series. So this is the sawtooth curve and the square wave printed as a sort of, as you move down the piece, you get more and more terms of the Fourier series, and you see how that affects them. And this is the same thing with, I think this is one of the Weierstrass functions, which I think in the limit is supposed to be nowhere differentiable. A similar sort of idea of sort of seeing how the structure builds up. And this was from last spring. Somebody decided they wanted to make a Hoberman sphere, so they made a Hoberman sphere for their final project. This is just a quote from another mathematical artist, George Hart. The more math you know, the more stuff you can make, which is absolutely true. So let's see. Given the time, I think I'm going to skip through virtual reality. I think I'm not going to spend much time on it. This is a three-dimensional virtual reality experience in three-dimensional hyperbolic space. And this is there's sort of a map over here. Again, there's an effective holonomy here. You walk around a square in the real world, and you only walk around 4 sides of the right-angled pentagon in the virtual world. And you have to take one more step to get back to the start. And there's sort of more recent versions of this, of that code, which we have views from within all of the 8 Thurston geometries simulated. But yeah, so this is nil, and you can see these sort of like terrifying mirages in the distance because of the way that the geodesics come back together in nil. And this is Sol, which is maybe the hardest one to calculate, and again, it has terrifying things happening in the distance. Oh, right, and here we're back in Euclidean space, except we're in the 3 torus as a Dane twist is being acted on. So I don't know if it's pleasant to be undergoing a Dane twist. I suspect it may not be. Okay, so the last 10 or so minutes, I want to say a little bit about spherical video. So what is spherical video? So this is they're sometimes also called 360 video or 360 cameras. So so this is a video I took a few years ago on the campus of Stanford University. I'm juggling here with a few friends. And this is showing the video that we took in the application that comes with the camera. So I'm able to rotate around and look in all directions. The way this works actually is that the camera has 2 fisheye lenses that see around 190 degrees. And so they overlap, and then it's possible to stitch those images together afterwards. So I can look everywhere that I want. You can see down here, this is the tripod that the camera was sitting on. And then up above, you see there's a lamp in the ceiling here, and I can look in all directions. So that's what it looks like when you're in the app. What does it look like if you just open up this video on your hard drive? So anytime you've got anything on your any image or any video, it's in a rectangle. That's the way images are stored on our computers. And so you have to take the sphere of data and make it flat. So it's another way to project from the sphere to the plane. And this time it's using equirectangular projection, so latitude and longitude. So this is the equator around the camera. And down here you can see that this is the tripod. So this is the south pole. It's getting stretched out along here. So 90 degrees south, every point in longitude gives you the same position. And up here, that's the light that was up in the ceiling. So I got interested in this technology, thinking about the ways in which we should transform spherical images and spherical video. So if you have an ordinary flat image, then, and you want to zoom in on something, then it's obvious what to do. You just scale up the image, crop in the boundary, and there you go. But on a sphere, what are you supposed to do? What does it need to scale? There's no way to crop anyway, because it's a sphere already. It's a closed manifold. There is no boundary. So the right way to do it, in my opinion, is to view the sphere as the Riemann sphere and then apply conformal transformations to it. So what you're seeing here is pulling back the image that this is the same video, I'm just repeating it again, after it's been pulled back through the function z goes to z squared. So that squares everything. Because it's conformal, people are not, faces are not distorted, they're just rotated and shrunk. And so the video looks good. And now we have a pattern with 6 jugglers instead of 3. So if you turn up to juggling and you really wanted to do this pattern with 6 people, but you only have 3 people, then if the pattern has the right symmetry, maybe you can do it anyway. So I've got a couple of things to show, just a couple of videos, and then I'll stop. And let me just play this video, and then I'll say a little bit about what's going on. A past version of me. So, as I was saying, my name is Henry Segerman. This is a spherical Droster video. So you're sort of slowly zooming this way, or rather the frame here is coming over you this way, and over there's a sort of weird pedal portal in the middle of my apartment. This is the future, so there's future versions of me over there, and this is the past. So I'll hand you off to a past version of me to explain again what's going on. A past version of me. So, as I was saying, my name is Henry Segerman. This is a spherical Droster video. So as I was saying, so this is a repeating video. And this is using so I mentioned before, what should zoom mean if what does it mean to zoom into a point on a spherical image? And this is what it means. So this is the conformal transformation, which I guess corresponds to hyperbolic translation in H3. On the Riemann sphere or the complex plane, all you're doing is you're just scaling the numbers up. You're scaling the complex plane up by a scalar. So that zooms you towards 0 and away from infinity. And so, so with a little bit of rotation, we're zooming towards this point on the sphere and away from this point on the sphere. And so there's the camera looks like it's moving, but it's really not. Here's the tripod, where the tripod is not moving at all, but the zooming effect really feels like motion. So maybe there's some applications there. Of course, I'm doing some camera trickery, some video editing trickery. So there's a window in my apartment that I've cut out, and I've put 30 seconds in the past over here, and that means that I have to put 30 seconds in the future over here, and then that's how this video works. Okay. I've got one more. This is the last video I want to show you. It's about 4 minutes long. Hopefully that'll give us enough time. This is joint work with Vi Hart. And so I'll just let this play for a little bit, and then I'll say a few words, and then I'll finish. was a lot going on there. Let me just say a couple of words and then I'll stop. So here we go. So maybe one thing to notice, so there's 3 versions of Vi. There was 3 copies of Vi. There's also, I guess, 3 copies of a piano, except for this key. You never press this key. Terrible things will happen if you press this key. But there are only 2 copies of me. There's a version of me over here and a version of me over there, and that's it. There is no 3rd copy of me. Also, let's look at the sheet music. So I just handed the sheet music to Vi through the piano. She then puts it down on the music stand. She plays a couple of notes, picks up a hammer for some reason, and then she picks it up from, well, a different version of her picks it up from the music stand, plays a couple more notes, hands it to me, and then we're back at the start. I hand it to Vi through the piano. So there's only 1 copy of the music sheet. There are only 2 copies of me. How is this possible? So the musical form here is the form of a round, which is usually, traditionally, you have 3 different singers who are singing the same parts offset in time from each other. Here, Vi is singing all 3 parts offset in time by some clever editing, and the idea here was to have a visual representation of that same structure of the round with the piano, and then the other choreography on top of that. The mathematical transformation here, of course, is z goes to z cubed instead of z goes to z squared. And there's a lot more to how we ended up making this. This is on YouTube. You can look up piece for triple piano, PEACE for a triple piano, and then there's a making of as well. But I will say thank you for your attention, and I will stop there.
Thank you very much. Maybe we first thank our speaker first, and then we start from people in the room. Do you have any questions, maybe? Or maybe I'll start from something very simple, like your dice. I remember I'm fortunate enough to like see many of the stuff before, and then are they going to be stable if they are like not skewed? Like you have one tangent.
Yeah, so I mean, the symmetry requires that they have to be as stable on any face as they are on any other face, right? Yeah. So there's no difference in the stability of, right? It's no easier for any to roll from one face to another than it is in any other order. The symmetry is sort of what's giving you the fairness of the dice.
I see. So any other?
Thanks for the talks. I saw that some of the presented projects are linkages. So I want to ask, are all of them required a theoretical study before establishing them, or it might be designed by intuition only?
Yeah. Yeah, so let me see if I can go back and look at some of these. So these ones, this really, we needed to realize what the property of, so this doesn't, so given a self-similar tiling by quadrilaterals, you can try and do this to make it into a linkage with that shape, but most of them don't work. They jam up, and you actually require that the shape of the quadrilateral is cyclic, that the vertices lie on a circle. And this was not all obvious when we started. And so that really did require, I mean, we tried to make something and it didn't work. And we didn't know why, and then we figured out why it was. So that really did require some theoretical insight. These structures, this was more really just sort of intuitive or just playing around with the software to discover that this was possible, or maybe just to say that just a single beam was possible. But I knew that in order to do this sort of in order to be able to expand out to make a triply periodic three-dimensional thing, you needed some sort of beam that could expand or contract and have some sort of structure like this. And then, once you know about symmetries and the different kinds of lattices, then that gives you then you know sort of what things to aim for and what things to go to next.
Thank you.
Thank you for a very nice talk. I was wondering, does any of these structures appear in nature?
Good question. I mean,
biology or
yeah. So I mean, speaking broadly, negative curvature shows up all over the place in lettuce, kale, different corals, and yeah. I mean, there's I'm forgetting the name of the sea creatures that sort of ripple along, and it seems that they're playing with, they're putting very little effort in and using the sort of the way in which negatively curved surface has to sort of there are sort of stresses inherent in how it's embedded in space, and they're using those stresses to locomote with. So certainly negative curvature shows up all over the place. I'm not sure about things like self-similarity. I mean, obviously there are lots of fractal objects in nature. Maybe not this particular kind of tiling, but what was it? Right, these sorts of things. I mean, there's various kinds of broccoli, plants which have this kind of fractal structure, and so yeah, I mean, there's certainly some analogs there. I guess if you really stretch, you can go for nodding in DNA. If you want to see, I don't know if there are any DNA optical illusions there. Probably not. Yeah, and that's an interesting question. I mean, it's this. I guess as I was saying before, the reason that I'm doing this is not for applications or to see that there's a relation to something in the real world. It's just because it's there, and it's interesting.
About the white object that was just on screen, I think 34 on slide 34. That
the negatively curved, yeah.
Yeah, so that cannot lay flat on the table. Is that right?
Correct. So you can see that there's a patch which appears to be laying flat, and the hinges here are very loose. When you print in place, so I mentioned that this was printed in one object. When you do that, you have to leave a gap between the rod and the barrel of any hinge. So there's some looseness there which allows it to lay flat, but as you go further out, it always buckles up. There's no way to lay it flat.
Okay, thanks. I was wondering how that looks when it comes out of the 3D printer or during the printing process.
Yeah, well, so it would take me a little time to find it, but I would be able to show you like the 3D model, and it's we found by an iterative method a configuration for it in which all of the shapes are correct, and I mean, yeah, it looks sort of like it looks sort of like it does in real life, except in real life it tends to crinkle until it crashes into itself, and of course you don't want that if you're printing it, because where it's in contact with itself, it would be solid, and so it's just a little bit more. Imagine this, but in zero gravity, so it's just sort of floating in space, and that's what it looks like.
I see. Thank you.
We have an online question. Okay, from Ravindran. I'm not sure if I'm pronouncing the name right, but do you want to maybe unmute and then ask yourself?
Hello, am I audible?
Yes.
Yeah, I am from an engineering background, and it was a very interesting talk. Like this made me wonder about some of the power transmission mechanisms in automobiles. So I was thinking, like, can you come up with some kind of mathematical measure of estimating the efficiency of the transmission from any of these designs?
Right.
Have you ever thought
I imagine that the efficiency is going to be very bad, right? This is, it's probably not a good idea to try and power anything that's going to be useful in the real world using these sorts of things. I guess certainly the triple gear. This is not because there's no way to there's no way to sort of put an axle in these because they sort of pass through each other. So yes, for many of these things, I think they're not going to work well. I haven't thought about the theoretical. I haven't thought about it, and again, that's for people who are real engineers to do that. But it's an interesting question. I mean, I think it's worthwhile, looking outside of the standard catalog of engineering solutions, to see maybe if there are things that people have missed. I think maybe the closest to something that really, does, I think, have the potential for practical use is this one. Just because, I mean, it's not that different from, so like scissor lifts, cherry pickers. If you need to get up high to clean a window or whatever it would be, you see these all over the place. And I think this is actually just a straight up improvement because it has, the ordinary scissor linkage is weak to sort of bending out of plane, and this really isn't. They support each other. But again, I haven't done any sort of numerical calculations to support that.
Okay, thank you so much.
If anybody would like to, I'd be very happy to talk to them. And,
sure, I'll get back to you. Thank you.
Yeah.
Thank you.
And any questions online? Maybe you can unmute yourself and ask.
Yes, may I ask a question?
Sure.
No, very interesting talk indeed. My primary question is about the rolling knot, which appeared early in the talk.
Yeah.
The mathematical explanation was like there were no 3 points which lie on a plane. Hence,
no tritangent planes, yeah.
Exactly. But so my first question is whether or not there exists space of solution for such rolling knots, meaning that you can generate systematically a family of such rolling knots. And the second question is, the knot theory is a very three-dimensional phenomenon, meaning that when you go higher space, you can just go around, there's no knot. Is there any counterpart in higher dimensions that you have treated?
Oh. Yeah. So okay. So to both of the questions, the answer is I don't know, but I'll try and say something. Yeah. So my understanding is that the only known examples of this sort of thing are for the trefoil with this particular kind of configuration. It's not clear to me exactly what right? How do you parameterize a knot? I mean, it's an infinite dimensional space, so how do you describe this in a sensible way? So I'm not sure. I will say that the way that I designed this particular shape was to take the stereographic projection of the standard torus knot in S3, and then I had to modify it because, and this still isn't perfect because it has a problem with the center of gravity goes up and down, which you don't want, right? You want the center of gravity to be horizontal. Laura Tallman is another mathematician who's done a whole bunch of things with 3D printing. I think she's looked more carefully at trying to solve that, to constrain it so that that's true as well. But yeah, so to my knowledge, there are no other examples known, but also no proofs that there are no others. And in higher dimensions, I have not heard of anything. That's an interesting question. I guess the equivalent would be that a knotted surface should have no tritangent, quadtangent, presumably quadtangent hyperspaces. But again, I've never heard of any work along those lines. That's an interesting question.
Thank you very much.
Normally, finish here, and then let's thank Harry again.
Thank you.